All right, let me go through the slides and make sure I touch base on a couple of things before we go into your lab. This lab is going to be the study of binary search is going to be spread across 2 labs. So we're not going to implement everything about binary search trees today, but I want to go over at least what you want. You want to be able to determine if the binary tree is empty. Hey, how do you do that? Yeah, in roots, no. Okay, that was great. Search the binary tree for a particular item. Hopefully y'all can figure out how we go about doing that. I've already set up in order. Yes, you can hopefully take it from there. Insert an item into the binary tree, aka add. One function we didn't get to today, and will not get to, is deleting an item from a binary tree. Can be somewhat tricky, but if you do it a certain way, it's not too bad. Find the height of a binary tree. Ooh, how would we do that?
Keep going. You go to every single one.
Binary tree, just to check like how many levels there are.
Yeah, so, but you're doing this recursive call, so it's the the most number of recursive calls you've done is one way to get to it. What would be another way to do it?
Could you just take the print function you had and say like add one to like a call, like how many times we've done it, and then just return that?
Right. Remember, guys, this is a function call, so you can add at the very end of this, int level, and then increment level every time you go down a level. It's a recursive call. That's perfectly fine. So that's one way to do it. What's a different way of doing it? Whenever I say what is a different way to do it, the first thing you should think of is how could we store a variable to keep track of it? It could be a class variable, and how would we update it? Every time you add, right. And you'd also have to update it when you delete as well. But we haven't done delete, so those are 2 ways to do height. By the way, you are doing height for this lab. You're not doing remove, so I'm going to let you all figure that out. Yes?
So to clarify, what does height refer to? Does that refer to the amount of elements, or how many, would that height be 3 up there on that balance?
Okay, hold on. Height can mean many different things, because that's a great question. For our lab, returns the height of binary tree. Great. That's beautiful. Womp, 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 womp. Okay. Oh, man. I will have to get back to you, but intuitively, what's the height of this? 3 is what I would say. I would call this height 3, because you have 1, 2, 3. If I put a node right here, what's your height? 4. If I put 1 right here, what's your height? 4. It's still 4. So it's how many levels there are. Quick question. How many elements or nodes can you put on each level? If I gave you level and I parameterized it on level X, how many items can there be?
Level minus 1.
Yeah, 2 to the level minus 1. So up here, it's 2 to the 1 minus 1, aka 2 to the 0, aka 1. Down here you got 2 to the 2 minus 1, which is equal to 2 to the 1, aka 2. Down here you got 2 to the 3 minus 1, which is equal to 2 to the 2, aka 4. So down here is what? 2 to the 3rd, oops, that's it. Wrote that backwards. 8, 16, 32, 64. Another reason why every time you go left or right, you're cutting it in half, because these levels can contain more and more. Any questions? Okay, cool. All right, let's see. Find the number of nodes in the binary tree. Hopefully you can do that by just traversing through it and finding out. Find the number of leaves. Hey, we didn't say what a leaf was. What do you think a leaf is inside of a binary tree?
Like an end one which points to 2 nodes.
Right. So is this a leaf? Is he a leaf?
Yeah.
No. Is he a leaf? Is the 45 a leaf?
Yes.
Ah, see, he has no children. A leaf is a childless node. Because he's at the, the end of the tree where the leaf would be. Everyone got it?
Mars.
All right, all right. Be able to traverse, we talked about that, and copy binary tree. I'm going to let y'all figure that one out, but how could you do this? Well, yes. Yeah, traverse the entire tree and just call add every time. right?
Yeah.
Now, if you want it to be the exact replica of the tree, when would you call add? In order. Well, no, you'd want to do it pre-order. Yeah, that way it would put it. There you go. But either way, it's going to be fine. Okay, I think we talked about that. Searching's great. Inserting, which is called adding, and next we'll get to delete next time. Okay. Any questions about the binary search tree we did today, or the binary search tree we did today, or the code we went over today? Yes.
So if we had a value that was like two values that were equal to each other, like say we had two twos, how would that? I know it's probably something simple, but just to see it, how would that look? So we go to the left.
Well, yeah, because you could say greater than, it could go here, or it could go to the right of 0.
Okay.
You go, either spot's actually fine, because,
Either way, it'll still work out.
yeah, as long as you're consistent with which side it's on, yes.
So like if you just had a bunch of the, like let's say if you just had a bunch of the same values,
Mhm.
like it would, there would be a way to identify one value from another from the level, right? Is that kind of,
Oh,
like 2 up there and the 2 at the bottom, they're
Or-
different, like you're able.
they were
The
at,
same-
they were probably, well,
the
no, there's
same
really no
value.
way, nothing that distinguishes them at all. Now, in our current implementation, you could say that this 2 was added before that 2, but once you get to further implementations, you could not say that that was the case. There's no real difference here. Yes.
Could that 0 realistically get placed there based on what we coded today?
Well, 0 is greater than negative 22, right?
Mm-hmm.
Yeah.
Okay.
Because it's less than 2, greater than 22, there's a 0.
Oh,
Okay? All right. Let's go over